So in this video, we will discuss about the laws of refraction according to wave theory of light. For that, let me consider two media like this. Let this be the rarer medium and this be the denser medium. Let AB, call this as AB be the interface or the line separating this rarer medium from the denser medium. Now let me consider two parallel rays like this. Okay, let this ray originate from the point X and this ray from Y. Also, let me draw a perpendicular at this point like this. Let's mark this point as some C and this point as some D, and let this point be some E. Okay, this one is 90, this also is 90. Clearly the parallel rays, that is XC and XD, YE are equal. By symmetry we know XC is equal to YE. This is Y, right? Because also these two rays are in the rarer medium, so they have the same velocity. Let the velocity be V1. Okay, now after the point C, this ray has to enter to the denser medium. But after the point E, the second ray remains in the rarer medium itself. Is that clear? After the point C, this ray has to move towards the denser medium. So let me mark the point C here. This is C. Okay, so that I can draw the normal in here. Now let me draw the normal through the point C. Normal is always perpendicular to the interface. Now actually this ray has to move like this. This should be the actual path of the ray. But because of refraction, because it is traveling from the rarer to denser medium, this ray bent towards the normal. Now it won't take this straight path, it will bend like this. Okay, so this should be the path. Let me take some point in here, let's say CF. Let me erase some part of this line. I'll explain it. I'll explain why this CF is less than ED. Clearly, we know the ray CF is traveling with a velocity V2. Since it is in a denser medium, we know V2 is less than V1. Clear? And let us assume by the time the ray from E or the wave from E reach the point T, that is time ED, that is the time taken by the ray to reach the point D from E, the ray from C reach the point F. Let's assume these two time period are equal, T. Now if I multiply T in this inequality, we have V2 into T less than V1 into T. Clearly, we know V2, velocity into time, will give the V1 into T means the velocity into time, that is the length ED, the distance ED. Clear? Similarly, V2 into T means the distance in the denser medium, that is CF. So CF is less than EF. sorry, ED. Clear? So this length will be greater since the velocity is higher in the rarer medium. That's the anomaly in here. CF is a little smaller than ED. Now I need to draw the, see, this is the incident wavefront. And by Huygens principle, we know wavefront is always perpendicular to the ray. So this is the incident wavefront. Now I have to draw the refracted wavefront. For that, I have to use again the Huygens principle. See, at the point C, this CF is actually V2 into T. So what I have to do is I have to draw a circle or draw an arc with the CF as the radius, keeping the C as center, or keeping the pointer of the compass at the point C. That is, I have to draw an arc like this. Remember, the CF is the radius, which is equal to V2T. This is the radius. Okay, and C is the center of the circle. Now, as I said before, by the time the wave from C reached the point F, the wave from E only reached the point D. So the wave from D just started. Okay, so that I can take a point in here. Okay, now how will I draw the refracted wavefront? What I have to do is I have to connect these two such that this line should be tangent to this arc. Okay. Now this gives me the refracted wavefront. Okay, this is the incident wavefront CE, and we have FD, the refracted wavefront. Now let me erase all this. Now when you look at here, we have this as the angle of incidence. That means the angle made by the incident ray with the normal. Now we know this angle is 90. That will make this angle 90 minus I. And this angle is also 90. Clear? That is, normal is always perpendicular to the surface. And that will make this angle I. Then only we have 90 minus I plus I will be 90. This I and I will get cancelled. So this angle will be 90 when this angle is I. Clear? This also is 90. Clear? Because the ray is perpendicular to the wavefront. Now coming to the angle of refraction, this is the angle of refraction, R. Since this angle is 90, we have this angle 90 minus R. Clear? This angle. Now we know this angle is 90 again. That is, the refracted ray is always perpendicular to the refracted wavefront. In order to make the sum of the angles of a triangle 180, this angle should be R. Then only 90 minus R plus R is 90. That 90 plus 90 will make the angle sum property, that is the sum of the angles of a triangle 180. Clear? Now see, this point is C. Okay, this is C. You cannot see here. This is C. Now consider triangle CED. When I take sine of angle of incidence in that triangle, that is sine I, we know by the definition of sine of an angle, sine I is opposite side. This is the opposite side by hypotenuse. Hypotenuse will always be opposite to 90. Side opposite to 90 is this one. So sin I is ED divided by CD. Clear? But we know ED is equal to V1T by CD. Let's put that as equation number 1. Now consider triangle C. Let's take this point as some C. This is actually F. Okay, F is here. It is hidden inside this 90 degree. So consider this triangle CFD. We have sin R. Like before, sin R is opposite side, that is CF, divided by the hypotenuse of this triangle is opposite to 90, that is opposite to 90 means this side itself. Again this side CD. Equal to, we know CF is actually V2 into D. V2 into T divided by CD. Call that as equation number 2. Now sin I divided by sin R is actually V1T divided by CD divided by V2T divided by CD. This is equal to V1T by CD. You can reverse this, take the reciprocal and multiply CD into V2T. So cancel this CD, also this T. You will get sin I divided by sin R is equal to V1 by V2. That is actually, if I take the refractive index of denser as mu2 and the refractive index of rarer as mu1, that is actually mu2 divided by mu1. V1 by V2 is actually mu2 by mu1. Okay, since the light is traveling from rarer to denser. So this can also be written as refractive index of second medium with respect to first medium. This one is actually Snell's law. This one is actually the Snell's law. So we have derived sin I by sin R is the refractive index of second medium, that is denser medium with respect to rarer medium. This is actually Snell's law. Okay.